No matter what kind of computer security system you're using, the first step is often identification and authentication. Who are you and can you prove it? Once a computer knows that, it can figure out what you are and are not allowed to do. Access control can't start until identification and authentication is finished. Let's talk briefly about what the user recognition problem is. Alice has some ability on a computer and we want to make sure that only she has that ability. Sometimes the ability is access to some information, files, account balances, and so forth. Sometimes the ability is access to the entire computer. No one else can turn the computer on and use her data or programs. Sometimes the ability is more explicit, withdrawing money from an ATM using a cell phone or stopping a burglar alarm from ringing. Sometimes the ability is on a website, access a calendar or her brokerage account among the millions of things you can do on the web. Sometimes the ability is access to a cryptographic key that is just too large for to remember. Some systems use access control measures to protect private keys. It doesn't matter what the ability is, what's important is that some access control measure is required to identify Alice. Actually, the access control measure has to do two things. It has to allow Alice in and it has to keep others out. Doing only one is easy. An open door will let Alice and everyone else in. A bricked over door will keep others as well as Alice out, but doing both at the same time is harder. We need something that will recognize Alice and let her in, but will be hard for others to duplicate. We need to be able to identify Alice and then authenticate that identification. Actually, the access control measure has to do a third thing, keep a good audit record of what happened, but this is not important right now. Traditionally, identification and authentication measures have centered on one of three things. Something you know, something you are, or something you have. These roughly translate to passwords, biometrics, and access tokens. Sometimes systems use two of these things together. Paranoid systems use all three. The traditional approach to authentication is a password. You see it everywhere. When you log on to a computer system, you type in a username and password. To withdraw money from an ATM, you put your card in the slot and type in your PIN. The two steps in each of those examples mirror the title of the previous slide. The first step is called identification. You tell the computer who you are. The second step is called authentication. You prove to the computer that you are who you say you are. The computer at the other end of these transactions has a list of usernames and passwords. Once you have entered in your username and password, the computer compares your input against the entries stored on the list. If you enter a valid username and the correct corresponding password, you're in. If you don't, you're out. Sometimes the system will again prompt you for a username and password. Sometimes the system will lock up after a certain number of bad attempts. You wouldn't want someone to be able to steal an ATM card and then try all 10,000 possible PIN codes, one after another, in an attempt to find the correct one. Unfortunately, the system of username and password works less well than people believe. The whole notion of passwords is based on an oxymoron. The idea is to have a random string that is easy to remember. Unfortunately, if it's easy to remember, it's something non-random. And if it's random, then it's not easy to remember. For example, check out this XKCD comic demonstrating the duality between easy to remember and not random. It turns out that random, unrelated words together often form a better passphrase than what systems guide the users to create. A password is a form of user-remembered key, and dictionary attacks against passwords are surprisingly effective. How does this attack work? Think about an access control system for a computer or website. The computer has a file of usernames and passwords. If an attacker got her hands on that file, she would learn every password. In the mid-1970s, computer security experts came up with a better solution. Instead of storing all the passwords in a file, they would store a cryptographic hash of the password. Now, when Alice types her password into the computer or website, the software computes the hash of the password and compares that hash with the hash stored in a file. Therefore, there is no file of passwords to steal. There is only a file of hashed passwords. And since a hash function prevents someone from going backward, the attacker can't recover the passwords from the hashed passwords. Here's where dictionary attacks come in. Assume that an attacker has a copy of the hashed password file. He takes a dictionary and computes the hash of every word in the dictionary. If the hashed word matches any of the password entries, then he has found a password. After he tries all words, he tries reverse dictionary words with some letters capitalized, and so forth. Eventually he tries all character combinations shorter than some length. Dictionary attacks used to be hard because computers were slow. They're much easier now because computers are a lot faster. Some have dealt with this problem by requiring stronger and stronger passwords. What this means is that the password is harder to guess and less likely to appear in a password dictionary. Some systems generate passwords randomly for users by concatenating random syllables to create pronounceable passwords. Passphrases are recommended to be complex sentences with nonsense thrown in. There is a maximum to the entropy that the average computer user is willing to remember. You can't expect him to memorize a 32-character random hexadecimal string, but that's what has to happen if he is to memorize a 128-bit key. As bad as passwords are, users will go out of the way to make it worse. If you ask them to choose a password, they'll choose a lousy one. If you force them to choose a good one, they'll write it on a post-it note and stick it on their computer monitor. If you ask them to change it, they'll change it back to the password they changed it from last month. And they'll choose the same password for multiple applications. Want to steal a bunch of passwords? Put up a website with something interesting on it. Porn, hockey scores, stock tips, or whatever will appeal to the demographic you're after. Don't charge for it, but make people register a username and password in order to see the information. Then sit back and collect usernames and passwords. You would be surprised how many different services you would be able to log into. Passwords are something the user knows. Other authentication techniques are based on something the user is a biometric. It's a simple idea, you are your own authenticator. Your voiceprint unlocks the door of your house. Your retinal scan lets you in the corporate offices. Your thumbprint logs you onto your computer. It's even used in Star Trek. Captain Picard signs those electronic memo pads with his thumbprint. Biometrics are the oldest form of identification. Thousands of years ago in China, fingerprints were used on all business documents in the same way signatures are used today, to provide approval of the document or authorization to perform any actions that the document outlines. Physical recognition is a biometric. Our ancestors used that even before they evolved into humans, and you can see cats spraying to mark their territory for the same reason. Biometrics are also used for identification in communications systems. On the telephone, your voice identifies you to the person on the other end of the line. On a contract, your signature identifies you as the person who signed it. Your photograph identifies you as the person who owns a particular passport. For most applications, biometrics need to be stored in a database like passwords. Biometrics are great because they are really hard to forge. It's hard to put a false fingerprint on your finger or make your retina look like someone else's. On the other hand, biometrics are lousy because they are so easy to forge. It's easy to steal a biometric after the measurement is taken. The moral is that biometrics work great only if the verifier can verify two things. One, that the biometric came from the person at the time of verification, and two, that the biometric matches the master biometric on file. The third solution to proving identity is to use something you have, a physical token of some sort. This is an old form of access control. A physical key restricted access to a chest, a room, a building. There are several basic ways this can be done. Most simply, the holder can just prove that he is holding the token. Computers that require a physical key to turn them on work in this manner, so do computers that require a smart card. The most serious problem with this system is that tokens can be stolen. If someone steals your house keys, for example, she can unlock your house. So the system doesn't really authenticate the person, it authenticates the token. In addition to stealing a token, someone can copy it. Some tokens can be easily copied, physical keys, for example. Another problem is that there needs to be some authenticated way of determining that the token is really there. This problem can be illustrated using credit cards. It's difficult to forge a physical credit card, which makes it risky to use a forged credit card to purchase things at a store. It's far easier to use a forged credit card over the telephone, however. If talking about a computer system, how do we actually read a token? Your phone may have a fingerprint scanner, but what about a smart card reader? Two different technologies deal with this situation. In challenge reply systems, the token is a pocket calculator with a numeric keypad and small screen. When the user wants to log in, the remote host presents him with a challenge. He types that challenge into his token. The token calculates the appropriate reply, which he types into the computer and sends to the host. The host also does the same calculation. If they match, the user is authenticated. In time-based systems, the token is the same pocket calculator, but it only has a screen and no keypad. The numbers on the screen change regularly, generally once per minute. The host asks the user to type in what is showing on his screen. If it matches what the host expects, he is authenticated. A full system probably also includes a password. The basic idea is that some secret calculation is going on inside the token that can't be impersonated. One last token needs discussion. The password, but this time written down. There is a knee-jerk reaction to writing passwords down in the security community, but if done properly, this can improve security considerably. Someone who writes his password down turns something he knows into something he has. This trick does allow him to use longer passwords, which can make passwords actually secure again. It does have all the problems of a simple token. It can be copied or stolen. It doesn't work if Alice writes her password on a yellow sticky attached to her monitor. Much better is for her to put her passwords in her wallet. This can be secure. Probably the best solution is to have two parts to the password. One part remembered by Alice and the other part written down in her wallet.